Hello and welcome to the Computer Vision Festival, hosted by the AI Accelerator Institute, a global community of over 400,000 AI leaders and practitioners, all striving towards one shared goal: inspiring the next generation of machine intelligence. With expert presentations on the festival agenda covering everything from space exploration on Mars to self-supervised learning, you're in for a treat. If you have any questions for our speakers or want to connect with them further, then ask away in the comment sections of the video and hear them answered at the end of each session in our live Q&As. If throughout the day you're loving the content, then be sure to check out the AI membership plans, where you can get access to exclusive content in the form of interviews, reports and articles. Access all areas passes to all past and future events. You can also join our Slack community, which is home to more than 2,500 fellow AI, machine learning and computer vision professionals, and is full of dynamic conversations and contributions. So if you're not already a member, come and join us today. Sign up using the link on the AI Accelerator Institute website. I want to say a massive thank you to all of our sponsors and partners for helping us to bring the festival to your screens today. Our amazing speakers for contributing some awesome content, and to you, our attendees, for joining us today. That's it from us, so go ahead, sit back, relax, and enjoy the festival.
Indeed. Okay, so everyone, as we speak, Alex is just being populated into the room. So yeah, welcome back everyone to the fourth session of the Computer Vision Festival on day one. I hope you're all having a great time so far. Super excited about our next speaker and the next presentation. So we have Alex, who is a Chief Science Officer from Tensor Vision Technologies and also a Senior Fellow at UCLA. And the session today that she is here to speak to you on is Casual Explanations in Computer Graphics, Computer Vision, and Machine Learning. Like I said, super excited about this one. And on that note, I'll leave it over to you, Alex.
Thank you so very much for the introduction. It is causal explanation. There's nothing casual about this. This is quite formal. And it is causal explanations for data-driven decision in a tensor framework. Now, data-driven decisions are ubiquitous. In every type of industry requires explanations for the data-driven decision, from chemometrics, econometrics, neuroscience, bioinformatics, computer graphics, surveillance technologies. They are everywhere. For example, as a result of the amount of data-driven decisions, the EU has passed the General Data Protection Regulation. These are set of laws governing decision-making by complex algorithms, and legal scholars have interpreted this particular legislation as to include a right to an explanation. Meaning that the algorithm has a right to be heard, an opportunity to be heard, and gives humans the opportunity to contest decisions of an algorithm. In the US, you have both local and federal governments joining the Open Data Initiative, making data access available to everyone in order to have transparent government. Now, data is very huge amounts of it, but in order to make transparent government truly transparent, you need a set of tools that enable data scientists, journalists, and citizens to analyze public resources, question public policy, and discover hidden knowledge that's useful for social, scientific, or business initiatives. And these tools, in order to be meaningful, they have to be delivering causal explanations. At Tensor Vision, we argue that developing causal explanations for correct results or for failures from mathematical equations and data is important in developing a trustworthy AI and retaining public trust. So we've been developing a causal data analysis pipeline that is data agnostic, not specifically to a particular type of data. Although we primarily work with imaging data, we've also worked with sound. We've also worked with human joint angle over time, but it's really truly data agnostic. So we're going to go over some of this. Now, causality is a highly misunderstood concept, despite the fact that we use it in our everyday lives to make decisions. For example, causality is often confused with correlation. For instance, there was an article that discussed the preschool diet of children and the likelihood of risk of breast cancer as an adult. And it says, for one additional serving of French fries per week, the odds ratio of breast cancer was 1.27. That means a weak association. Now, Katie Couric, a journalist in the US, has asked the question, does eating French fries cause breast cancer? Walking an incredibly thin line. She's not saying that it does cause cancer, but she's simply asking the question. On the other hand, Reuters completely gets it wrong. They say children who eat French fries raise their breast cancer risk. Well, if it's just simply two variables that are associated, not causal, you cannot increase the breast cancer risk because they're just associations, not causations. Another article has discussed predicting predicting how likely a couple is going to get divorced based on the way they spoke to one another. And they have longitudinal clinical studies, and based on the type of vocal acoustics, they could predict things very well. Now, prediction doesn't necessarily mean causation. If you're speaking to your spouse in a disrespectful manner, if you're speaking loudly, that may be because you have there's infidelity in the marriage, or because there's financial problems. It doesn't. These are they have a common cause that impact the likelihood that you're going to be polite to your spouse, or rude, or aggressive in your manner of speech, and the likelihood to get divorced. So these common cause impact these two variables: the way you speak to one another and the likelihood of getting divorced. And of course, popular press gets this concept wrong and says, well, if you just speak politely to your spouse, you are not likely to get divorced. Well, it doesn't no matter how politely you speak to your spouse, if there's infidelity in the marriage, that doesn't mean that you have somehow made your marriage divorce-proof. Now, you might think, okay, so clearly it's popular press that's getting things wrong, but it can happen even in scientific circles with people who know better. For example, there's a scientific article that it clearly states in the abstract that we are evaluating the association between mortality and out-of-hospital hypertension and hypoxia separately and in combination. The association, right? So not causation. We are evaluating the association between mortality and out-of-hospital hypertension and hypoxia. Unfortunately, the title of the article uses causal language. The effect of combined out-of-hospital hypertension and hypoxia on mortality. The effect of something on something, it's cause and effect. You can only have an effect if those variables are known to be causal. And someone, of course, wrote to the scientific journal saying, well, there's a history of medicine that illustrates the harms of misconstruing association as a causal relationship. And this particular author points out that women have been prescribed estrogen replacement therapy in the belief that it would improve their cardiovascular health, because there were associations from observational studies. When in fact, when they've done causal studies, they found out not only does it not improve women's health, it actually increases their cancer risk. So words really matter. Getting this thing wrong can have detrimental effects. And in this case, the doctors meant well, but correlations and associations do not imply causation. So given all of these problems, it's not surprising that the field of causality has had somewhat of, has been treated with some disdain by many scientists. For example, Carl Pearson referred to causality as a fetish of modern science. That was in 1800s, but even as late as 1990s, you have Terry Speed saying causality should be treated the way it's always been treated in statistics, preferably not at all. Bent Munchen has said the research should abandon thinking and using terms as cause and effect. And they would be preferably and healthier if everyone stopped talking about causality. Well, a paradigm shift took place. One that basically says model not the distribution of the observed data, but model the mechanism of the generated data. And that will put you on sound scientific ground. So what does it mean to be modeling the distribution of the observed data? Here's our set of observations, and this is what conventional statistics and machine learning does. It tries to understand the things that it observes by comparison to modeling the mechanism that generated the data. Okay? So what is causality? Causality is the relationship between two events, A and B, where A causes B means the effect of A is B, a measurable and experimentally repeatable quantity. Causal inference is the process by which one uses data to make claims about the causal relationship. The causal field has three areas: a forward causal inference, an inverse causal inference, and the causal mathematical modeling that sustains these two areas of research. Forward causal inference is the estimation of effects of causes, and it asks the questions, what if? If a hypothesized or known causal factor X was changed by 1 delta unit, how much would Y be expected to change? Now, if X is indeed a causal variable of Y, then every time you change delta X, you would see a change in delta Y, in a delta amount change in Y. A sub-area of forward causal inference pertains to determining the correct experimental design, meaning how do you collect data such that you can make causal conclusions. A reverse causal inference, or the search for causes of effects, is also known as the why question. Donald Rubin has referred to it as a cocktail party chatter that is outside the realm of science. And this was in 1977. Since then, he has adjusted some of his thinking. His thinking has evolved, but there is merit to this question, despite the fact that he has his thinking has evolved, and we'll go over that in a bit. His former PhD student has softened Donald's stance and referred to reverse causal inference as a way of checking the causal model. It can serve as a motivation for the forward inference question. Now, one of the main dictums of causal inference, it says no causation without manipulation, treatment, or intervention. You have to physically, or if you're manipulating, you can either have a physical intervention in the real world, or you have an intervention on the model, meaning you're doing a counterfactual. Only then can you derive causal explanations. So here's an example of causal inference. In this case, this is a very specific example to give you an idea. You have in the case of facial images, A facial image is the compositional consequence of several causal factors, and that is scene structure, illumination, and camera. The scene structure, meaning the overall geometry, is also the result of the person, age, and expression. This is known as the forward causal model, but often we're interested in the inverse causal model. So hopefully to all of you, if you develop the forward causal model by changing, by modifying each causal factor in turn, and developing a forward causal model, then you are, in order to compute the causal factors from an unlabeled data set, you means that you have to invert the forward causal model. There has been some misunderstandings about this in machine learning, and people have often taken unsupervised data, unlabeled data, and ran algorithms that have and predicted causal values. Well, prediction is not the same thing as causation. In any causal factors, one computes from unlabeled data without inverting the forward causal model. Might get you causal explanations, but there are no guarantees to it. Any such discussion, any causal explanations are, if they happen to be true, they're purely coincidental. To make certain that we all understand why it's important to develop the forward model first and invert it, let's talk about the why question and what makes it so difficult. So if you look at this image and someone says, why is this set of pixel reddish? Why do they have values 12800, meaning red, green, and blue? Red has value 128, and can have values between 0 and 255, where 0 is black, 255 is the brightest red, and the same thing for green, 0 to 255, and so on. Well, if you were to look at this, one answer can say, someone can ask, well, why is it that way? And you can answer, because the sensor behind the lens has sensitivity. And the person, no, I don't want to know about the camera sensor. I want to know, why is the pixel reddish and not white like the wall? Because, and you can sort of answer, well, because the unobserved red light, so white light hits the binder, the unabsorbed red bounces off the binder onto the wall and then bounces back into the camera. This is a light transport question. And the person can continue, well, yeah, but why is the pixel reddish, not bright red, when the wall happens to be the way it would be when the wall is made out of aluminum, or it's a mirror? So you go, so you're asking about the material properties. In one case, you have the wall happens to be diffuse, has diffuse properties, while the mirror is specular, or the aluminum is specular. And the person asking the question might still not be convinced and say, yes, but still, if the binder was closer to the wall, it was still darker, would be sort of more bright red, or if you had a ball, again, it would be more bright red than it is right now. Why is it that right now it has these specific values, and why do they change if you sort of tilt the binder more closely towards the wall? So now you're asking about the scene structure. So I hope you noticed, by asking a simple question like, why are these pixel reddish? There are at least 4 different ways of answering the question. And each one of these why questions imply a different experimental design, grabbing data off the internet and hoping to be able to answer any of these whys in a way that, with some guarantees that they're correct, is very difficult. You need to have captured the data in a systematic way for each one of these questions. Now, you can address each question separately or together. So the why question requires context, and a forward causal model provides it. Every one of these why questions has a slightly different experimental design, meaning a slightly different data acquisition involved. Now, one of the reasons that Donald Rubin has referred to the why question as the as the cocktail party chatter problem, often because the same set of causal factors, different combinations of them, give rise to exactly the same image or the same output. In computer vision, this is known as visual illusions. So you can have two different geometries can give rise to exactly the same image. This person could be a young woman where the camera is somewhere from behind, or an older woman where the camera is at 90 degrees to the face. Often, these visual illusions can be broken if you have an additional image from a different viewpoint or a different illumination. Human visual system is remarkably robust to these types of problems, but when they happen, we really find them compelling. So, for example, is this a dog or is this a man? So there are multiple combinations that can give rise. So just in case you thought it's just drawings, this is an actual image. In this case, you have two possible geometries from the same viewpoint, but the resolution is low enough that you can't quite tell if this is a dog or a person. And here's another one that is a little that will might give you more information. Out of curiosity, I hope the volume was, you heard the sound behind us, because if you didn't, then we're going to be, now, words, as I mentioned before, they matter. So rather than using the word reverse causal inference, we defined it as inverse causal inference. And the why question is, we provided a mathematical specification for it. Rather than saying that we're computing the reverse causal inference, we're computing the inverse causal inference, meaning we're estimating the causes from a set of effects given a forward model that we invert, plus a set of observations that constrain the solution set. In this way, we make the problem well posed. Now, often people might think, well, isn't it enough to have a prediction model that is very accurate? Why do I need a causal explanation? Why does that matter? And as a result, I've decided to show you this video of Richard Feynman that talks about knowing some information and understanding information and why it matters.
Now, another thing that people often say is that for guessing two identical theories, suppose you have two theories, A and B, which look completely different psychologically, different ideas in them and so on, but then all the consequences that are computed, are exactly the same. They say they use an agreement experiment. The point is, though, that the two theories, although they sound different at the beginning, have all consequences the same. It's easy usually to prove that mathematically by doing a little mathematics ahead of time to show that the logic from this one and this one will always be a corresponding consequence. Suppose we have two such theories, how are we going to decide which one is right? No way, not by science. Because they both agree with experiments to the same extent, there's no way to distinguish one. So two theories, although they have deeply different ideas behind them, may be mathematically identical, and they usually people say then in science it should take one doesn't know how to distinguish them, and that's right. However, for psychological reasons, in order to get new theories, these two things are very far from equivalent, because one gives a man different ideas than the other. By putting the theory in a certain kind of framework, you get an idea what to change, which would be something, for instance, in theory A that talks about something, that you say, I'll change that idea here. But to find out what the corresponding thing is you're going to change in here may be very complicated. It may not be a simple idea. In other words, a simple change here makes maybe a very different theory than a simple change there. In other words, although they're identical before they're changed, there are certain ways of changing one which look natural, which don't look natural in the other. Therefore, psychologically, we must keep all the theories in our head. And every theoretical physicist that's any good knows 6 or 7 different theoretical representations for exactly the same physics, and knows that they're all equivalent, and that nobody is ever going to be able to decide which one is right at that level, but he keeps them in his head hoping that they'll give him different ideas to begin with. Incidentally, that reminds me of another case, and that is that the philosophy or the ideas around the theory, a lot of ideas. You say, I believe there is a space-time or something like that in order to trust your analysis. And these ideas change enormously when there are very tiny changes in the theory. In other words, for instance, Newton's ideas about space and time agree with experiment very well. But in order to get the correct motion of the orbit of Mercury, which was a tiny, tiny difference, the difference in the character of the theory with which you started was enormous. These are so simple and so perfect. They produce definite results. In order to get something to produce a little different result, it has to be completely different. You can't make imperfections on a perfect thing. You have to have another perfect thing. So the philosophical ideas between Newton's theory of gravitation and Einstein's theory of gravitation are enormous. The differences, rather, are enormous. What are these philosophies? These philosophies are really tricky ways to compute consequences quickly. A philosophy, which is sometimes called an understanding of the law, is simply a way that a person holds the laws in his mind so as to get quickly at consequences. Some people have said, and it's true, for instance, in the case of Maxwell's equations and other equations, never mind the philosophy, never mind anything of this kind, just get the equations. The problem is only to compute the answers so that they agree with experiment, and it's not necessary to have a philosophy or argue or worries about the equation. That's true in a sense, yes and no. It's good in the sense you maybe, if you only get the equation, you're not prejudicing yourself and you'll get better. On the other hand, maybe the philosophy helps you to get it. It's very hard to say. For those people who insist, however, that the only thing that's important is that the theory agrees with experiment, I would like to make an imaginary discussion between a Mayan astronomer and a student. The Mayans were able to calculate with great precision the predictions, for example, for eclipses and the position of the moon in the sky, the position of Venus, and so on. However, it was all done by arithmetic. To count certain numbers, to subtract some numbers, and so on. There was no discussion of what the moon was. There wasn't even a discussion of the idea that it went around. There was only calculate the time when there would be an eclipse or the time when it would rise, the full moon, when it would rise, half moon, and so on. Just calculating only. Suppose that a young man went to the astronomer and said, I have an idea. Maybe those things are going around, and there are balls of rocks out there. You could calculate how they move in a completely different way. You just calculate what time they appear in the sky and so on. So, of course, the Mayan astronomer said, yes. How accurate can you predict eclipses? He said, I haven't developed the thing very far. But we can calculate eclipses more accurately than you can with your model, and so you must not pay any attention to the mathematics scheme is better. And there's a very strong tendency of people to say against some idea, if someone comes up with an idea and says, let's suppose the world is this way, and you say to him, well, what would you get for the answer to such and such a problem? And he says, I haven't developed it far enough. And you say, well, we have already developed much further, and we can get the answers very accurately. So it is a problem as to whether or not to worry about philosophies behind ideas.
So I'm hoping that his explanation of the discussion between a Mayan astronomer and a student might give you a good understanding of the importance of modeling the mechanism that has generated the data rather than merely computing a set of predictions when something is true or not. So to think about it, traditional statistics versus causal inference. Traditional statistics and traditional machine learning, it's about associations. You're modeling the distribution of the data. You predict given observations, given two variables that may be causal or may just simply two variables that are associated with one another. You predict one from the other. You predict how likely someone is to get divorced based on the acoustics of their speech, rather than modeling the mechanism that got you to a point where you are using acoustics that when you're yelling to your significant other. Causal inference, by comparison, is about causation. You're modeling the mechanism that generated the data, and you predict results from interventions. So you have to do an intervention either in the real world or on the model itself. Now, natural images are the composite consequence of multiple constituent factors related to scene structure, illumination, and imaging. And multilinear algebra, the algebra of higher order tensor, is a transparent framework that facilitates the analysis of the causal structure of image formation. And I've already showed you this. So the person, the age, the expression determine the scene structure, the illumination, the camera determine the final image. You want to learn the model that has generated this data, which is a forward model, and then invert it in order to compute the inverse one. Now, data acquisition, in order to establish a causal relationship between observed data and the causal factors, you can do so by acquiring a data set, a training data set, which is acquired by varying each causal factor in turn while holding the rest of them fixed. Of course, the best evidence for causation comes from randomized comparative studies. So what do I mean by data acquisition? In case of facial images, you have a person and you are varying the viewpoint systematically, and for every viewpoint you vary the illumination. And this data set can be organized into a data tensor. In this case, this is a third order tensor. A data tensor is an n-way array. In this case, this is an n-way array, a hypercube of data, of numbers. In this case, at every entry, so you have illuminations by views, by people, and at every entry you place in there a vectorized image. And this is done, if you notice, in a very systematic way, right? You acquire the data very thoughtfully and systematically. And after you've acquired this type of data, you perform a tensor decomposition that decomposes the image in terms of the person parameters, the illumination parameters, and the viewing parameters. So every image contains information. By using the M-mode SVD, you can now get back the latent information, the constructs that represent the person, the viewpoint, and the illumination. So for example, you have one woman, and for this woman, in this case, this is a tensor decomposition that you have computed from training data. This is variance in viewpoint, variance in people, variance in illumination, and this is multiplied by a illumination representation, a viewing representation, and a person's signature. The interesting about this is that no matter how you change the illumination and the viewpoint, the person's signature never changes. It is a statistically invariant representation to all the other causal factors. And when you have multiple images, every image has the same person representation, but so these images were captured at the same event, the illumination is the same. The only thing that differs is the viewpoint. So you now have a viewpoint, a different viewpoint. So every row is a different viewpoint representing these images. Now, when you have this type of decomposition, you are literally taking an image and decomposing it into the causal factors. You can, if you throw out the illumination information, what type, so I have said that you can decompose it in this way, but let's say you have removed the illumination information. Is it really statistically invariant? Is the illumination representation truly just capturing illumination information, or will it have an impact on the rest of the data? So we've looked at different types of data. We've done a dimensional reduction in illumination representation, and we've noticed that from the original image, the only thing that was missing when we reconstructed the data was the shadow. We can, over here, we lost the shadow and the shading. Right? So there's something very predictable about doing tensor factorization, tensor factor analysis. You can throw out information that is strictly with a particular causal factor that may not, that sort of gets in the way of doing some specific task. In this case, illumination does hide a lot of the facial features. And here's another example showing the same thing. Now, when you have this type of examples, when you can change, when you have a unique representation for the person, you can also change the expression at will by taking the expression from someone else. And this is one of the things that our colleagues have done in the past. So this is, you take the images and you decompose them into the person representation and the expression. And now we're mapping the expression of the other woman onto so this is sort of kind of called, these days, this was done for entertainment, but it can also be fake data. So that can cause some problems in society. Now, this type of decomposition tends to also have not just, it's not can be used just simply for mischief, but it can be used for meaningful tasks in computer graphics. Often in computer graphics, if you want to generate a 5-minute computer graphics video clip, it can take up to a month to render. So one of the things that a lot of computer graphics scientists do, there's some pieces of the geometry that they sort of approximate coarsely. Like imagine the tree trunk can be coarsely approximated by a cylinder, and then you want to map a texture around it, or you want to have the skin. You don't necessarily want to sit and sort of develop every single pore of the skin of someone. You just want to have the right texture for it. And if you can sort of get rid of as much of geometry complexity, and you just want to have the correct texture onto the data. And you want the texture to change as the camera changes, as the illumination changes. So if the sun is setting, then shadows have to appear the correct way. If you're looking at something from a different angle, again, you want to have everything appear correctly. So here's the entire system from data acquisition, analysis, and new synthesis.
Image-based texture mapping technique. We begin by acquiring several images of a 3D scene from different viewpoints and illuminations. These images are rectified and assembled into an image data tensor. Each column of this 3-mode tensor spans the image texels. Each row spans different illuminations. The third mode spans different viewpoints. The data tensor is an organized set of training images which sparsely sample the viewing and illumination spheres. From these training images, the tensor texture method learns a generative model of the bidirectional texture function, including complex details such as self-occlusion and self-shadowing. Mathematically, tensor textures is a multilinear model. To compute it, the data tensor is decomposed using a 3-mode singular value decomposition, The decomposition yields a tensor texture basis. Using this basis, our method can quickly synthesize textures from arbitrary viewpoints and illuminations. Each image is represented as the n-mode product of the tensor textures with the viewpoint and illumination representations. In the following animation, the coins are a tensor texture mapped onto a simple planar surface. However, it invokes an impression of 3D relief as we vary the viewpoint and illumination.
So this looks like it's 3D, but we're quickly mapping a planar texture, onto a plane. And it looks correct. The viewpoint looks correct. The illumination looks correct as you're changing. You're quickly mapping one after the other. So, but the geometry is very coarse. It's a perfect plane. And in this example,
the cone kernels are a tensor texture mapped on a simple surface.
Notice the cone kernels are all pointing forwards. But if you're going to map it around the cylinder, they need to sort of, the cone kernels have to be changing, facing in the correct direction. So we mentioned that in the previous example, we had different viewpoints. So the texture would change with the viewpoint. But in this case, every column in that texture has a different viewpoint relative to the camera. So rather than just the entire image. And of course, all the discussion we've had so far has been about global representations. But often we find ourselves that we don't have enough data, or you acquire data in a thoughtful, systematic manner is expensive. But you can acquire a small data set. However, and you want to leverage that data set by creating a counterfactual model that allows you to represent more information. For example, an object, you can change the viewpoint illumination for an object like the face, but you also realize, well, the object really is made up of a recursive hierarchy of parts and wholes, right? So you have the eyes, you have eyelashes, you have the nose, the mouth, all of these things make up a face. And if you could just represent the eyes, nose, and mouth separately and somehow combine them together to represent new data, it can be much more effective. So for example, in this case, we would like to decompose this image in terms of the eyes, nose, and mouth. So rather than representing the entire face, you want to represent each piece and then somehow combine them together. So normally you take your image and you vectorize it, and you can think of this, here are my pixels or my measurements, and you have people by viewpoints, and you can have another axis by illumination. You can take this and then subdivide it into parts, and you can have a bag of parts. But in reality, you need to do something a little bit more, because you get information from the whole as much as you get from the parts. The whole can tell you information. You can have whether somebody's gender, somebody's age, not just simply, okay, eyes, nose, mouth. You can have those exactly same parts to different, both men and women, but yet somehow when they're put together on a woman, they somehow look different. So there's this idea that you can get more information, not just simply from the parts, but also from the entire whole. So one way to do this, you can decompose the data as follows. You can split up the pieces and then add them up together. So you have a bunch of identity matrices that simply that have a way of adding them together. You can represent them. So you have represented your data tensor into a hierarchical data tensor. It's simply a way of rewriting it such that when you multiply with the identity matrices, which are basically like it's a type of addition, ends up being exactly the original data tensor. But because you're separating them into pieces, you can now have a hierarchical variance, viewpoint, people, illuminations for each individual part. So these are the eyes, for the nose, and the full face. And therefore, the representation is you have information for the full face, how the different features are organized on the face, the eyes, the nose, and so on. Every single part, you have a signature for every single piece of the face. Now, this is known as a hierarchical block tensor faces, and it's very similar to what you currently see in machine learning, in deep learning, where you have these low-level features, mid-level, and high-level features. Now, the discussion we've had so far has been used faces primarily, but exactly the same type of tensor decomposition, tensor acquisition and decomposition can be applied to lots of types of data. For example, human motion. You have people by activities, by joint angles over time, where the people could be, the person can have a normal gait or some kind of pathology. And you can have the person walking, going up the stairs, down the stairs, and looking at the different joint angles and computing a human motion signature for different pathologies. Or you can do it for computer graphics, learning the Charlie Chaplin style in walking, and can you transfer that style doing a different activity that you haven't seen him, going up the stairs, down the stairs. You can imagine taking Charlie Chaplin's walk and decompose it into the style versus the activity itself. And you can also look at 3D sound by placing different microphones, by different speakers in different locations, and capturing that information as it arrives to your ears, and help you in order to create a surround sound system or a way of using this information to navigate in an environment. So this is not just simply for entertainment, but it also can be used for neuroscience and looking at brain signatures over time, fMRI data over time. Now, in terms of the human motion, here's a quick example to give you an idea. This is someone, so imagine every joint angle is really the difference from one person to another is the amplitude of that joint angle. So imagine if I have a stiff knee, that my knee simply won't bend. So the angle is always 0. But otherwise, from one person to another, it's pretty much the same thing. You're bending the knee, you're extending the leg, extending it. So it's always the same motion. The difference is how much you're swing, how much of an angle you're performing, how much are you swinging your hips, how much are you bending your knees or don't bend your knees. That really makes the entire motion signature. And I want to show you a small toy example, and then we can look at something more realistic. In this case, you're looking at a basket. Basket has high amplitude, going up the stairs, then down the stairs. This is soccer, which tends to be low to the ground. And this is bouncy. Bouncy has to have something, an in-between kind of motion. And at this point, you want to synthesize the information going down. You've seen a couple of examples going up the on the ground, up the stairs, and from that you extract the motion signature and then use it to map it to something you haven't seen before. Now let's look at something for a normal human motion. So you start with someone walking that has a specific signature. You extract the signature from that walk and you map it going up the stairs. Oops. Now, final words. Correlation does not imply causation, and neither does prediction. Causal explanations are very important for scenarios where, for medicine, where things matter, for security, like surveillance technologies, there's certain set of types of information that you cannot just simply use prediction. You need a causal explanation. Thank you.
Can you hear me? Hey, Alex, can you hear me?